Namaste dosto. Imagine you are playing a video game where your character can move not just left and right or forward and backward, but also fly up and down. How do you keep track of exactly where your character is? That's where the three-dimensional coordinate system comes in. Today, we'll explore the very basics of this system which helps us locate any point in space. Ready? Let's dive in. In three-dimensional geometry, we use a system called the right-handed Cartesian coordinate system. It has three axes, the x-axis, y-axis, and z-axis, and all of them are perpendicular to each other. Think of them like three sticks meeting at right angles, creating space all around. Each of these axes lies along a real number line, stretching infinitely in both directions. Where all three axes meet, we have the origin, which we denote as capital O with coordinates 0, 0, 0. Remember, that's O of 0, 0, 0. Now, these axes also give us directions in space. The x-axis is like going left or right, the y-axis is forward or backward, and the z-axis is up or down. So, if you want to tell someone where exactly a point is in space, you give them a set of three numbers, a triplet, written as x, y, z. This triplet is unique for every point, meaning no two points share the exact same triplet. Picture a box in your mind with three lines meeting at the corner. That corner is the origin, and the edges are the axes. This three-dimensional system is the foundation for all 3D geometry. Allez, isn't space suddenly more understandable? Let's continue by zooming in on those three axes x, y, and z and see what makes them special. Each axis stretches infinitely in both directions through the origin, like invisible number lines floating in space. When you move along the x-axis, only the x-coordinate changes while y and z remain 0. That means points on the x-axis look like this, x, 0, 0. Similarly, the y-axis contains points where only the y value changes, so these have coordinates 0, y, 0. And the z-axis has points 0, 0, z, only the z-coordinate varies. Now here's a cool bit. These three axes are pairwise perpendicular, meaning each one meets the others at right angles. In physics and maths, we often represent their directions with unit vectors, little arrows of length 1, called I hat for x, j hat for y, and k hat for z. So when you're moving in 3D space, you can think of moving in the I, j, and k directions, left, right, forward, backward, and up, down respectively. This framework is essential for working with any 3D problems in maths or physics. Excellent, Beta, you're getting the hang of this. Now that we know about the axis, let's talk about the planes formed between these axes. Imagine a flat surface stretching infinitely in two directions. Each pair of coordinate axes defines such a plane by fixing the third coordinate to 0. For example, the xy plane is where the z coordinate is 0. So every point here has coordinates x, y, 0. This plane stretches left, right, and forward, backward, but has no height. Next is the yz plane, where the x coordinate is 0. Points here look like 0, y, z, so this plane extends forward, backward, and up, down. Finally, the zx plane holds the y coordinate at 0, so points here are x, 0, z. This plane covers left, right, and up, down directions. Visualizing these planes helps us understand how space is divided and how points relate to each reference plane. Think of these planes like flat floors, walls, and ceilings that slice through the 3D world. Shabash! You are doing great so far. Ready to add a twist? The three coordinate planes don't just float in space, they divide the entire 3D world into 8 separate regions called octants. If you remember, in 2D, two axes divide a plane into 4 quadrants. In 3D, it's like stacking those planes, producing 8 pieces of space. Each octant is defined by the signs of the coordinates, whether x, y, and z are positive or negative. For example, the first octant is where all 3 coordinates, x, y, and z, are positive numbers. As you cross from one octant to another, one or more of these signs change from positive to negative, just like crossing quadrants in 2D but now with an extra dimension. Thinking about octants helps immensely when solving geometry problems or plotting points in space. So next time you see an octant, you'll know exactly which corner of the 3D space you're in. Great job! Let's bring all this together by seeing how you locate a point in 3D space. Any point is described by its ordered triplet, that's the 3 numbers in parentheses indicating x, y, and z. Each coordinate tells you how far the point is from a reference plane. Specifically, x shows the signed distance from the yz plane, meaning how far left or right the point is. Similarly, y is the distance from the xz plane, telling you how much forward or backward it is. And z is how high or low the point is from the xy plane. Imagine dropping perpendicular lines from the point straight onto each of the 3 axes to find those distances. This method ensures a precise location in space. So, if you see a point P with coordinates x, y, z, you can think of it as the intersection of 3 perpendicular lines projecting from each axis. Isn't it like a perfect 3-dimensional address? Allez va! To wrap up, let's quickly remember the key ideas we covered. The x-axis is made up of points with coordinates x, 0, 0, and the y-axis has points 0, y, 0, and the z-axis contains points 0, 0, z. All 3 meet at the origin, which is 0, 0, 0. Then, we have 3 coordinate planes, the xy plane where z is 0, the yz plane where x is 0, and the zx plane where y is 0. These planes divide space into 8 octants, each defined by positive and negative signs of coordinates. And to locate any point in 3D space, we use that neat ordered triplet, projecting perpendicularly from all 3 axes. Soch ke dekho, this system isn't just maths, it's how we navigate and understand the 3-dimensional world around us, from architecture to animation to astronomy. Keep practicing these concepts, and you'll find the 3D coordinate system becoming second nature, helping you solve complex space problems with ease. Shabash!